Hi guys, good evening.
Good evening, sir.
Good evening. Let's
Good evening,
get
sir.
started. Yeah, good evening. Let's get started. So we are in this chapter that is basics of finite difference method. So till now we looked at essentially how to form or obtain spatial derivatives given a stencil. Right? So we were able to calculate first derivative to second order accuracy, second derivative to second order accuracy, and so on. So we also looked at what is the modified wave number approach. Then we essentially looked at, so in this we looked at basically backward differencing schemes, forward differencing schemes, and then central differencing schemes. Then we looked at how to calculate the truncation error um, for a given equation, right? And then, so we were able to calculate what is the truncation error of a particular scheme. So we were able to calculate, what will be the order delta t and order delta x for a given equation and for a given scheme, right? We were able to discretize given an equation and scheme. We were able to calculate this, and then we were also able to comment on whether the scheme is consistent or not. Because as you reduce the delta t and delta x to smaller and smaller values, does the truncation go to zero, right? So we kind of did all of these things till now. So today we're going to look at we're going to look at the stability analysis. That is the von Neumann stability analysis. Okay, so this is the kind of the last topic in this chapter. So the stability analysis. So what we do in stability analysis is that whenever we deal with unsteady or iterative schemes, okay. So in these cases, we wish to know whether the round of errors that we have round of errors will whether they will grow from time step to time step or iteration to iteration. Okay. So we want to know whether they will grow or remain the same or shrink. Okay. So this is what we want to characterize, whether the round of errors that we have, are they going to stay the same, or they're going to grow, or they're going to shrink. We certainly do not want these round of errors to grow, because they're going to take over the solution, and then the solution will eventually be not useful, right? Because it will go to a very large value. If the round of errors stay the same, that means remain the same, or they shrink from time step to time step or iteration to iteration, then we would like to use such a method that is kind of, we call that such a method as a kind of a stable method. Okay. So we call such a method as a stable method. Otherwise, we're going to call the method as unstable, and we will not be able to use an unstable method to calculate anything that is required. Okay. So a stability analysis is kind of due to von Neumann, and what it does is it is applicable for simple one-dimensional and linear partial differential equations. Okay, so as you can see, this is only applicable for simple one-dimensional linear partial differential equations. Of course, but then it is actually not applicable, or it will get very complicated to do, not applicable for, let us say, in general, the equations that we deal with, let us say in fluid mechanics and or solid mechanics. Let us say if we consider the applicable for Euler's equations or the Navier-Stokes equations. So for all these general three-dimensional nonlinear partial differential equations that are kind of complicated, the stability analysis cannot be directly applied, right? Because the analysis is kind of gets very difficult, and then you won't be able to find whether the method is stable or not. However, we will still use the simple one-dimensional linear PDEs to or the schemes applied to these PDEs to guide us in essentially in choosing schemes for the general Navier-Stokes equations or Euler equations. So essentially, we use the insights from simple 1D PDEs to guide in choosing the methods for real life problems. Okay, so for real life problems or essentially equations and the methods. Okay, essentially we will be able to kind of choose them wisely from the insights or the conclusions that we draw from the applying the stability method to a simplified model. Okay, so that is the idea of this stability analysis. Okay, so let us consider the one-dimensional transient heat conduction equation. So we have one-dimensional transient heat conduction equation that we have been dealing with. Okay, which is basically given by partial u partial t equals alpha times partial square u by partial x square, where alpha is the thermal diffusivity, u is a kind of temperature, little t is the time, x is the spatial coordinate. Okay, so this is the partial differential equation that we have been dealing with. Now, of course, because we are applying the stability analysis, we need to choose a particular method, a particular discretization of this equation. So let us choose the explicit Euler's method. Okay, that is also known as forward time centered space. So I write this as FT1 CS2, saying that this is basically the first order accurate forward time and then second order accurate centered in space. Okay, that's what I'm choosing. So with this, we know how to write this discretization. This is basically ui n plus 1 minus ui n divided by delta t equals alpha times ui plus 1 minus 2 times ui plus ui minus 1, all of them obtained at time level of n. So this is your explicit Euler scheme, and we also remember how to write the implicit Euler and the Crank-Nicolson. If it is implicit Euler, then we know that the left-hand side remains the same, whereas on the right-hand side, we get everything at n plus 1, right? And then we know that for the Crank-Nicolson scheme, both the left-hand side and the right-hand side are evaluated at n plus half instead of at n or at n plus 1. And then accordingly, the time derivative and the right-hand side, the spatial derivative are accordingly changed, right? So we kind of, you can recall from the previous lecture. Okay, so now this is the finite difference equation that we have obtained, corresponding to the partial differential equation that we have here. Okay, all right. Then we go back to the definitions of these errors, right? So we define what is known as truncation error. Truncation error, if you may recall, we define this as the amount by which the exact analytical solution fails to satisfy the finite difference equations. Okay, so this is not going to be equal to 0, and this is what we called as the truncation error, right? We have used this principle in calculating the truncation error for these schemes in the previous lectures. Then we also have defined two more errors. One is called the discretization error. Discretization error, which is, we call it as DE. This if we were to call it as TE. So discretization error is the error between the exact analytical solution and the computed solution. Okay, so we're taking some norm of this thing. So where I can write essentially U is the exact analytical solution, and capital U is the discrete solution obtained on a computer. Okay, so this is what we have. And then we also have one more error that is known as the round-off error. Round-off error. This is essentially related to the round-off that happens for any floating point number in a computer, because we have to truncate it at some point and then kind of round it off, which you are familiar with while doing the assignment problem 1. So round-off error, if you were to denote using RE, this is basically the difference between the discretization error and the finite difference solution solved on a computer to the finite difference solution that is obtained on a computer with an infinite precision. So this is we already know, this is basically the same as this thing. Whereas U tilde, what I'm defining here is basically this is the discrete solution to the finite difference equation obtained on a computer with infinite precision. Means we have this hypothetical computer in which there is no round off. That means it can represent any floating point number to infinite precision. So there is no round off that is involved. So as a result, U tilde, when you try to solve the same equation, this equation on an infinite precision computers, hypothetically if we have one, then that solution is going to be U tilde. Whereas if you solve it on a regular computer, then the solution is going to be U. Okay. Now, the only difference between these two is that you are still solving the same finite difference equation, one on a regular computer with some precision, whereas the other one is the infinite precision. So as a result, the difference between these two is the round off error, right? That is where you are rounding off the floating point numbers. Okay. Now, because each of these solutions, so then I can also define what is my round off error.
So I have a question over here.
Yeah, go ahead.
So basically, this is that analytical solution that we are talking of. So you have in the beginning of this lecture, you have told that there are some partial differential equations is very impossible to solve like analytically because it's too complicated in nature.
Correct.
So suppose if I don't know what I mean to say is exact solution of that. So even this term is also a hypothetical term. There's what I mean to say is like what is the significance of that then in that way? If I'm not able to solve it analytically, then this small u is also basically assumed number in that way, right, sir?
No. So if you are not able to solve this, then you will not have little u available. This is not available. Then actually you won't be able to calculate what is the discretization error in your problem.
But the things are like that only. So if I'm not wrong, that suppose if I want to do some solve a problem which is very difficult in nature.
Yeah, true.
So I will not be able to calculate the exact analytical solution for that. Is not it?
Correct. Yes, that is true.
Then this the term is discretization error is become like a small u is a hypothetical thing. I'm not able to get it anyway in the practical world.
Correct.
And u I can get. So there is no meaning of u minus capital U.
No, the thing is, there is still meaning because you will be able to calculate this for example, for this one-dimensional heat equation, you can still calculate that. So this you can obtain analytically for this problem. And then for a range of problems, you'll be able to obtain. But then for all those problems where you won't be able to find, of course, you won't be able to find the exact analytical solution, then you cannot calculate this discretization error as such. But for all other problems, you'll be able to at least quantify the discretization error for certain schemes, for certain equations. But then for practical problems, you won't be able to calculate what is the discretization error because you would not know what is the exact analytical solution. In fact, if you had known that in the first place, you will not actually take the step to calculate it numerically.
Exactly.
Yeah. So, but then we still need to differentiate between this little u and capital U because they are not the same.
Right. So theoretically, we have to differentiate. Yes.
Yeah. So that is where the discretization error comes into play. Similarly, if you look at the round-off error, we can now argue that you have only access to a finite precision computer. You don't have access to this hypothetical infinite precision computer, right? So we don't have access. Then how can we calculate this round-off error? But then it turns out we can still define the round-off error in this fashion and then use the round-off error, which basically models how kind of the round-off error behaves in a computer So using that, we'll be able to quantify, and we will take the round of error as the leverage. You know, we kind of use the concept of round of error to determine whether a particular scheme is going to be stable or not, whether the errors are going to grow or decay. Although we don't know anything about the round of error. I mean, we only know, we won't be able to exactly quantify what is the round of error, but we will be able to model it somehow. I'll kind of come to that argument a little later. So, yeah.
Okay, sir. Understood, sir. No problem. Thank you.
Yeah.
Thank you so much.
Yeah. So we'll come to this. I think you'll probably have more questions in the context of round of error. Okay.
Sure.
So, yeah. So now I can define this round of error. Let me define it with some epsilon. Either I use this one or this one, okay, as essentially as u minus u tilde. Okay, now here we realize that each of this u tilde, and epsilon, all of these are kind of vector quantities, right? Because you're solving it on some domain, 1D domain, where it is basically a function of x. So these are all vector quantities. That means, you know, we know that there is some bar to it or something like that. So from here, I can now write what is my capital U equals u tilde plus epsilon. Okay, so this is the solution on a finite precision computer, and on the right hand side I have infinite precision computer solution, that is u tilde and the round of error. So if I add the round of error to the infinite precision computer, then I'm going to get the solution that I would obtain on a regular computer. I think that is kind of makes sense. Now let us go back and try to solve the equation, whatever we have, on a regular computer. Okay, so if we solve this equation, the discrete finite difference equation, then we know that this u actually will satisfy that equation. That means I can now go back and write this equation for capital U, because when you solve this equation on a finite precision computer, it's going to satisfy this u is going to satisfy this equation. Okay, so that means I can write the equation that capital U satisfies as u n plus 1 I minus u n divided by delta t equals alpha by delta x square, capital U I plus 1 minus 2 times u I plus u I minus 1, all of them at nth time level on the right hand side. Okay, so that's what we have. Then we also know that, let me call this equation some 1, okay, let me call it equation 2, okay, and call the previous equation as 1. So let's call this equation number 1, and then, okay, now we know that, let us say we solve this equation 1 on an infinite precision computer. Okay, then we know that the solution we obtained, that is u tilde, was obtained by solving it on by essentially solving this equation, you know, so that's going to be u tilde, right? It is also going to satisfy the same equation, u tilde I plus 1 minus 2 u I tilde plus u I minus 1 tilde, all of them at nth time level. Let's call this equation as 3. Okay, so essentially both u and u tilde are going to satisfy this finite difference equation. I mean, only when you solve it using this equation, the solution you would obtain eventually is different, because one of the computers is a finite precision, the other one is an infinite precision. Okay, so that is the only difference. But then now I can go back and then look at this equation 2, and then I'm going to substitute for u equals u tilde plus epsilon. Okay, so I'm going to substitute wherever is u, I'm going to substitute for u tilde plus epsilon. That's going to give me another equation by substituting that as u tilde I n plus 1 plus epsilon I n plus 1 minus u I n plus epsilon I n divided by delta t equals alpha by delta x square. On the right hand side I get u I plus 1 tilde n minus 2 u I n plus u I minus 1 tilde, all of them at n. And then plus I'm going to get also epsilon I plus 1 minus 2 times epsilon I plus epsilon I minus 1, all of them at time level n. Let's call this equation 4. Okay, so now what I have is only equation 2, I have just substituted for u equals u tilde plus epsilon. That's what I have substituted, okay, which gave me equation number 4. Okay, now I have these equations 3 and equation 4. Let me subtract off equation 3 from equation 4. Okay, so if I do that, what would I get? Essentially subtracting 3 from 4. So if I write 4 minus 3. This is essentially nothing but on the left hand side you have ui tilde n plus 1. There is ui tilde n plus 1. There is minus ui n minus un. So essentially all the ui terms in equation 3 will get cancelled. And then what remains is only the epsilon terms in equation 4 will remain. So which is going to be epsilon I n plus 1 minus epsilon I n divided by delta t equals alpha by delta x square. This is going to be epsilon I plus 1 minus 2 epsilon I plus epsilon I minus 1 at time level n on the right hand side. So this is the equation I got by subtracting off 3 from 4. Okay. Now what you see is that I got an equation. So this is the governing equation for error, right? We assume that, or this is the governing equation for error, or we can say for round of error to be specific. For the round of error, okay, to be specific. That means we have obtained a governing equation for the round of error from the governing equation for the primitive variable or for the solution variable. Now, what observation we make here is that the governing equation for the round of error is exactly the same as the governing equation for the solution that we are trying to seek, right? That is the temperature. Okay, so it's exactly looks the same. Of course, now the thing is that we want to know, does this error or the round of error, is it going to stay the same, or it is going to shrink, or it is going to grow, right? That's what we want to comment on, so that we can go back and then solve for this equation and then essentially obtain a solution, right? That is what our motivation is. But then what you see is that you got an equation for round of error. Solving it for, let us say, of course, we don't know what are the boundary conditions for the round of error, right? I don't know the boundary conditions. But even if I cook up some boundary conditions and then try to solve this equation, then what you see is that there is no point in solving this thing, because solving this thing is as complicated as solving the original equation itself. And then I don't know whether this equation is solvable or not, and so on. Okay. So as a result, we will not try to solve this equation directly the way we will solve the, governing equation for the solution variable. Rather, we want to still comment on whether the error is going to stay the same, remain the same, or it's going to shrink, or it's going to grow from this equation, together with some approximations for how this round of error is going to look like in both space and time. Okay. Now that is the main crux of this von Neumann stability analysis. So essentially now what we want to do is that we don't want to solve it like in a regular solution. Rather, we want to guess, or we want to still look at whether the round of error will grow or not. So what we are interested in is that the method will be stable if epsilon I at n plus 1 divided by epsilon I at n, the absolute value is less than 1, right? If this is less than 1, that means the error at n plus 1 is not growing with respect to the error at n. Okay, so either I can write epsilon I n plus 1 by epsilon I n. Then this is basically a stable method. If it is greater than 1, this is basically an unstable method. Okay, if it is equal to 1, this is essentially greater than or less than or equal to 1. This is basically a stable method. If it's greater than 1, it's unstable method. Okay, equal to 1 is basically neutral is stable. Okay, fine. But then how do I know how does epsilon is going to look like? So we need to come up with a model for epsilon. Okay, that means we need to come up with a model for the round of error. We're going to say the round of error is going to look like this. Okay, then we'll say, okay, if it is going to look like this, then we can calculate what is this ratio. Then that ratio will tell us, which is coming basically from this original equation. Then that ratio will obtain from this equation 5 is going to tell us whether the method is stable or not. Okay, so that is the overall idea. Now, so if we look at round of error, let us say in a computer, let us say if we are solving for a domain of length L. Okay, so if I plot how does the round of error look like, let us say this is the x direction. Let us say we are going from minus L by 2 to plus L by 2. And on the y-axis, if I plot the round of error, Okay. Then round of error essentially will look like something like this. Okay, something like this. So essentially it is going to be a random profile, right? It's going to be some random profile as a function of x. Now, so if we have any function like this, which let us say we call it as epsilon x, in general, the round of error is going to be a function of space and time because we are solving this PDE, right? In general, it's going to be a function of space and time. Let me introduce the time component a little later. So let me first look at how does it vary with space. So let me look at epsilon x. And then in general, if I have any arbitrary function, if we have any arbitrary function, we can always decompose it as a Fourier series. Okay, that means I can write this particular function epsilon x. It need not be this function. If you have any function, any continuous function, you can always represent it as a continuous series of Fourier series or Fourier terms. So we can write this as am times e to the power I k m x sigma. Okay, that means I have used this Fourier series with some coefficients and e to the power I k m x, where e to the power I k m x is basically nothing but cosine of k m x plus I sine k m x. Okay, where k m is the wave number. Okay, so what we're saying is that any function that we have can be represented as a linear superposition of sines and cosines, right? If I were to plot these sines and cosines, then by appropriately taking these magnitudes and then looking at different sines and cosines, their combination, I can represent any function, right? Essentially, the constructive and destructive interference of these sines and cosines will be such that eventually by the phase we consider and by the amplitudes, we're going to essentially we are going to reconstruct back this particular function that we are looking for. Okay, so that means this can be decomposed into an infinite sum of sines and cosines, like given by this equation. Now, okay, I think we have stumbled upon this idea before in the context of compact schemes and padded schemes. Let me give you a kind of again a little bit insights into this wave number. So let me consider a function, let us say y equals sine 2 pi x by lambda. Okay, let me consider 2 pi by lambda times x. So I consider this thing. Let us say we have a domain that is something like that, and then we have a domain of L. So this is minus L by 2 to plus L by 2. Okay, so so essentially I have this sine function. Let us say my lambda equals L. Okay, so that means this function has a wavelength of L. Then my profile or this function y is going to look like something like this. Okay, let us say it's going to look like something like that. Okay, so it is going from 1 second, better. Okay, so it is going from +1 to -1. Okay, in the y direction, and then this is your and it has a wavelength of L. Okay, it has a wavelength of L and it has a period of 2 pi in a wavelength of L. That's what it means. Similarly, if I look at another function, let us say y equals sine 2 pi by L by 2 times x. That means my wavelength equals L by 2. That means in a length of, that means let us say wavelength equals L by 2. Okay, let me introduce this thing. So I can compare this to y equals sine of km of x. Okay, so that means my km equals 2 pi by lambda. Okay, that's what I have. So my km equals 2 pi by lambda. In this case, lambda equals L. So that means my wave number km is 2 pi by L times 1. That means I can fit a period of 2 pi in a length of L, right? That's what I have. That means in a length of L, I can fit one such sine function. Okay. Similarly, if my lambda equals L by 2, then if I compare with sine of km of x, that means my km equals 2 pi by L times 2. Okay, that means we have 2 pi by L times 2. That means it is wave number is actually 2 times 2 pi by L. That means we can fit 2 such waves because in a period in a length of L. Okay, that means my sine 2 pi by L by 2x is going to look like this, right? Because I can now fit 2 waves, so my wave number is actually 2. That means if I can write in general y equals sine of km of x, where km is basically equal to 2 pi by L times m, where my m goes from 1, 2, 3 all the way to probably infinity. Okay, because then I can keep increasing my number of waves that I have in a period of length L, right? So that is how I can interpret this. Now we are doing this because we want to know how does sine kmx and cos kmx look like. Okay, so this exactly corroborates with what I have drawn here. Now, okay, now does it actually go to infinity? Now what will happen? So that means when I look at the lambda max, the lambda max we can have is L, right? As we have written here, that is the maximum wavelength I can have. That is the minimum wave number that we can have, right? Minimum wave number is k min equals 2 pi by L. Similarly, the minimum wavelength I can have is not infinity, right? Because I can only represent up to a distance of, let us say, if I have a grid of 3 points, I can put in essentially a sine wave that kind of fits like this, and this distance is going to be delta x, and this is delta x. That means I can have only a distance of 2 delta x to fit the to fit a kind of a sine or a cosine, right? So the minimum wavelength I can have is 2 delta x, which basically gives me the maximum wave number as 2 pi by L or 2 pi by lambda, right? 2 pi by lambda, that is equal to 2 pi by lambda min equals 2 pi by 2 delta x, that equals 2 pi by 2 times delta is L over n, right? L over n. Then I can write this as k max equals 2 pi by L times n over 2, right? So that means the maximum wave number I can have is only n by 2, right? So so m can go from 1, 2, 3 all the way to n by 2, where n is the number of grid points. Okay, so we can have up to n by 2 wave numbers, 2 pi by L times n by 2, that we can fit in, but anything not less than that, right? Because that is going to be one period. Okay, so that those are the two limits that we can have on the km or m, which is going from 1 to capital N by 2. Okay, any questions so far on this? I think we have done this before, but I'm just kind of trying to explain this again. So that means I can modify this summation to include the extent of m, right? So earlier I have written epsilon x equals, I have written epsilon x equals summation am e to the power I kmx, where m goes from now 1 to capital N by 2. That's all, right? It cannot go to infinity. It will stop at n by 2. Okay, so that's what we have. That means so this is the spatial variation of the round-off error. Okay, this is the spatial variation of round-off error. Okay, now we need to include the time dependence of the round-off error, because in general we write epsilon is a function of space and time, because we are solving for this one-dimensional transient heat conduction equation, which is a partial differential equation in space and time. Okay, typically if you look at in experiments, in done on, let's say, computer programs, what we see is that typically the round-off errors, if they kind of occur, I mean they will occur, they grow or decay exponentially. That means if you spot a round-off error, and for a, let us say, if the particular scheme is unstable, then the round of error, it would not take very long time for it to grow because it grows exponentially. It very quickly, let us say in few iterations, probably in 10 iterations, 20 iterations, the value is going to grow to very large value, right? Because it will kind of grow exponentially. So this is an observation that is coming from running several numerical simulations on a computer, okay, in the context of round of error. So then it makes sense to include the time dependence in the amplitude and say that this is essentially a function of am is a function of time, and then that is included as e to the power am times t, okay. That means we're going to write this as sigma m equals 1 to n by 2, e to the power am times t, e to the power I kmx, okay. So that's our equation, okay, or that's our model for the round of error. Okay, so essentially what we have done is we have not solved this equation because we said solving that equation is not useful because it is going to be consume the same amount of computational power, so we did not solve it. But then we made some certain arguments and then obtained the solution itself without actually solving it, okay. But then now we're going to, so essentially what we obtained is we obtained the solution, or we obtained the model for the solution. That means the solution is going to look like this is what we know. But then how does the solution behave when we try to solve the discrete equation that we have developed is what is going to give us whether this error is going to grow or not, okay. So that is the idea. So we now derived a model for the round of error and we have a discrete equation. We're going to now substitute this back into the equation and then solve for whether epsilon I at n plus 1 divided by epsilon I at n, okay, is going to grow or decay, is what we're going to observe, okay, by substituting this model, okay. But before doing that, what we have is we need to kind of simplify this even further. So if you recall, the equation we have discretized, that is this one, okay. So this is the governing equation we have. This equation is actually a linear equation. So this is a linear equation, linear algebraic equation, because there is no other coefficient here. Whatever the coefficient we have here, alpha is a is a constant value. So as a result, this is a linear equation. So when we have linear equations, we have one property that is linear superposition. That means if you have two solutions, the linear superposition of the two solutions is also a solution to the linear equation, right? So that is the superposition or linear superposition is the principle. That means if I have two solutions, S1 and S2, any linear combination of S1 and S2, that is alpha 1 times S1 plus alpha 2 times S2, is also a solution. Okay. So that is we have from the linear equations, because the governing finite difference equation is linear. We can study the behavior of the equation by using just one term of the solution. Okay, so what we are saying is that we have several terms here, right, going from m equals 1 to n by 2, but then because the governing equation is linear, what we are saying is that the behavior of one term is the same as the behavior of the entire series, okay. So as a result, we can discard all other terms and then just only work with one term. Now the question is, what does this mean? I mean, I have written something here. So it means if in this series, because everything is linear, we are saying that, okay, S1 is a solution, S2 is a solution, S3 is a solution, and so on. If either one of them starts growing, because it is linear combination, there are no nonlinear interaction. That means if S2 is growing, it is growing. It doesn't really change S1 as such, right? S1 either grows or decays at its own rate. Because of S2, it does not want to change S1. So as a result, if one term is growing, then the entire solution will grow because the entire solution is S2 is part of the entire solution. So as a result, the behavior of the series is same as behavior of one term. So that means we are going to look at that one term, which will either make the system to grow or decay, and then observe that if it is going to grow, then we say that the system is unstable. Okay, so that is the idea here. That means I'm going to out of the entire thing we have written here, that is epsilon of xt as e to the power. We have written several terms, sigma m equals 1 to n by 2, e to the power a m t, e to the power I k m x. Okay, so we're going to discard all these terms, only work with one term, that is epsilon m of x comma t as simply e to the power a t, e to the power I k x. Okay, so this is just one term of the above series, right? If this term behaves in an unstable way, then the entire solution is going to be unstable. Okay, so that is the argument we are making, and we could only do this because the governing finite differential equation is actually linear. Okay, yeah. Now one question, maybe let us say if it is nonlinear, then we won't be able to do this thing. Okay, but then can we linearize the equation and do it? We can linearize and do it, but it is not going to be kind of a faithful representation of the original nonlinear PDE in terms of stability. Okay, but we can somehow linearize it and then study to get some idea about whether the method is going to be stable or not. I think that people do. Okay, so that means now what I have done is we obtained a governing equation for error, which is the same as the governing equation for the quantity that we are solving for, that is temperature. Then we said this governing equation is too difficult to solve, or it is as difficult as the original problem itself. Then we said we will come up with a model for round-off error. Round-off error, how does round-off error look like? Round-off error looks like a random fluctuation, random function. Any random function can be written in terms of a sines and cosines using Fourier series. Then we have several terms in the Fourier series, out of which we discarded all the remaining terms other than m equals 1 to n by 2. We said they are not going to fit into the domain that we have discretized. And then we have this epsilon x comma t as e to the power a m t times e to the power I k m x. So this is the spatial variation. This is the time variation. Okay, that's what we have. And then we said that now, because the governing differential equation is linear, we can just study one term out of this, and that is going to give us the behavior of the entire series, right? That is what we are saying. Okay, now the question is, then we go back to our equation and then substitute for this value, and then look for whether our round-off error is going to increase or decrease. Okay, so that means I will rewrite the governing equation for the error. So the governing equation for error is given by epsilon I n plus 1 minus epsilon I n divided by delta t equals alpha by delta x square, epsilon I plus 1 at n minus 2 times epsilon I plus epsilon I minus 1. Okay, my epsilon is a little bit mixed up, so all of them are the same. Okay, so this is the governing equation for error. Okay, now I need to, of course, calculate what is E I n plus 1, epsilon I n, epsilon I plus 1 n, and so on from this model. Okay, that means if I want to calculate what is epsilon I n plus 1, this is nothing but epsilon m at x plus at just x, right, because it's at grid point I, and then time is t plus delta t. Okay, so that's going to be e to the power a t plus delta t. I'm substituting for t as t plus delta t in this equation, times e to the power I k x, right? That's what I have. This is at location x. Okay, similarly, let me calculate what is epsilon I n. This is going to be epsilon m at time t and space x. So this is going to be e to the power a t, e to the power I k x. Okay, similarly, let me calculate what is epsilon I plus 1 n, epsilon I plus 1 n. This is at a grid point of x plus delta x and time level of t. That is going to be e to the power a t, e to the power I k x plus delta x. Now epsilon I n we have already calculated. Then I need to calculate what is epsilon I minus 1 n. That is going to be epsilon I minus 1 m is going to be epsilon m. Because it is I minus 1, we are going to x minus delta x, and it is n, so this is at time level t. So this is going to be e to the power at, e to the power ik. In place of x, I'm substituting for x minus delta x. Okay. So that means I'm able to identify each and every variable in this thing. That means the error at different grid locations from this model for error that I have built, right, that I have assumed, okay, by valid arguments. Now I'm going to substitute for all these quantities into this equation, okay. So that's going to basically make it epsilon I n plus 1 minus epsilon n by delta t. That means this minus this by delta t. That is going to be e to the power a times t plus delta t, e to the power ikx minus epsilon in, that is e to the power at, e to the power ikx divided by delta t equals alpha by delta x square. On the right hand side, I have epsilon I plus 1n, that is e to the power at, e to the power ikx plus delta x is going to be e to the power at, e to the power ikx plus delta x minus 2 times epsilon in, that is e to the power at, e to the power ikx plus epsilon I n minus 1 n, that's going to be e to the power at, this quantity, e to the power ikx minus delta x. Okay, so this is the equation I have. Now what we note is that there are these e to the power at, e to the power ikx, that is there on both sides. So I'm going to take common e to the power at times e to the power ikx on the left hand side as well as on the right hand side. On the left hand side, I'm going to get e to the power at times e to the power ikx common, then it's going to be e to the power a delta t, that is what remains here, minus this becomes, entire quantity becomes 1 equals, let me send this delta to the right hand side. So let me write this as alpha delta t by delta x square. Okay. And then I will take out e to the power at times e to the power ikx as common. That means here what remains from in the first term is e to the power ik delta x minus, this is going to be minus just 2. And this is going to be plus e to the power at, e to the power ikx is taken out. Then this is going to be plus e to the power minus ik delta x. Okay. That's what remains. Okay, now I can cancel out what is e to the power at, e to the power ikx on both sides. And then what I have is e to the power at minus 1 equals, let's call this factor as some r times e to the power ik delta x plus e to the power minus ik delta x minus 2. Okay, so where r equals alpha delta t by delta x squared. Okay, this is some factor. Okay, so we obtained some equation here. But then what is our stability criteria? Stability criterion is epsilon m at spatial location x at time t plus delta t divided by epsilon m at spatial location x at time t. We want the magnitude or modulus of this to be less than or equal to 1. That is our condition. But then what is epsilon m at x comma t plus delta t? Using our model, this can be written as e to the power a t plus delta t times e to the power ikm or ikx divided by e to the power x comma t. This is going to be at e to the power ikx. Okay. Then this is nothing but e to the power a times delta t, right? Modulus of this is less than 1. Okay. So if let's call this as some factor g. Okay. So this is the amplification factor. Amplification factor happens to be just e to the power a times delta t, which we call it as g. So if this quantity in a absolute sense is less than 1, then we can say that the system is stable. Okay. If g is greater than or equal to greater than 1, if it is less than or equal to 1, we can call it stable. If g is greater than 1, we call this to be an unstable method. Okay, so that's what we have. Fine. Now going back, what we have is, this is the equation we obtained from the substituting the error model in the finite difference equation, right? So this is the error equation we obtained by substituting the error model in the final difference equation. Okay. So from here, now I want to study how does e power at behave. So for that, I need to kind of simplify this thing. So let me write down this equation again. So what we have is e to the power at minus 1 equals r times e to the power ikm delta x plus e to the power minus ik delta x minus 2. Okay. Now we know that e to the power I theta equals cos theta plus I sin theta. So in this case, let me call k delta x as theta. So then we know that e to the power minus I theta is equal to cos theta minus I sin theta. So if we're going to add these up, then e power I theta plus e power minus I theta is going to be 2 times cos theta. Okay. That means the summation of these two is nothing but 2 times cos of k delta x. Okay. This is 2 cos theta. That means e to the power at minus 1 equals r times 2 cos theta minus 2. That means 2r times cos theta minus 1. Okay. So this is cos theta. Okay. But then I will make it slightly more simplified so that we can find something from here. So this is nothing but e to the power at equals 1 plus 2r times cos theta minus 1. Okay, that's what we have. Okay, but then we can still again write 1 plus 2r times cos theta can be written as 2 or 1 minus 2 sine square theta by 2 is what I can write. Okay, then essentially what we have is this 1 gets cancelled with the minus 1. Then what we have is e to the power at equals 1 minus 4r sine square theta by 2. Okay. If I substitute for theta by 2, 4r sine square k delta x by 2. Okay, that's what we have. But then we said that this is e to the power at coming from the, by substituting the model for error into the governing equation. Okay, but we said that for the amplification factor, this modulus should be less than 1. That means this quantity for this particular scheme, that is modulus of minus 1 minus 4r sine square k delta x by 2 should be less than or equal to 1. Okay, so this is the condition that our delta t should satisfy in order for the method to be stable. Now, where is delta t in this? Delta t is absorbed into r, right? We have written r equals alpha delta t by delta x squared. So we need to obtain a condition such that if with that condition, we can then say whether this particular scheme is going to be stable or not stable and so on. Okay. So this is for the explicit Euler method. Okay, we have not yet obtained the condition, but we have obtained this intermediate condition, which is the 1 minus 4r sine square k delta x by 2. The modulus of that is less than or equal to 1. Okay, so that is the condition we have obtained. Okay, so we will, as we are out of time, I'm going to stop here. We will continue from here in the next lecture that is going to be on next week on Monday. Okay. If you have any questions, you can ask me now, or you can ask me through email or later anytime. Yeah.
Thank you, sir. Happy Deepavali to you, sir.
Yeah, thank you. Happy Deepavali to all of you as well.
Thank you, sir.
Okay, all right. We'll stop here. Thank you, guys. Talk to you later.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.